Hello, everyone. We are Team 28, and we present Project Kalman. My name is Dallas.
I'm Will.
I'm Andrew. To quickly go over the scope of our project, we wanted to perform a thorough analysis of the Kalman filter in three ways: lighting, movement depth, and obstruction handling for object tracking. After performing some initial testing on our filter build, we were looking on making improvements to its handling of object inclusion through the implementation of deep sort and other alternative methods to object tracking. Our implementation of deep sort came from a pre-existing model in Google Colab. The fundamental functionality of deep sort is to take in observed characteristics of an object in a video and frame its position through a bounding box, calculated through a convolutional neural network. In this case, YOLO 7. The model has some of the same issues with the common filter, given that it uses it as a base, such as like with motion blurring and stuff, but is much better at re-identifying objects correctly when encountering occlusion.
Okay, so let's talk a little bit about the results of our experiments with deep sort. Tracking an object when it disappears from view is no easy task. We clearly see here that even this state-of-the-art algorithm deep sort combined with YOLO V7, it loses track of the object when it's occluded. But after a great discussion with Professor Nguyen and some deep thought among our team, we realized that we needed to start thinking outside the box. Our first method involved getting crafty with the output of deep sort. So looking at the output here, we see one of deep sort's strengths, which is drawing bounding boxes for partially occluded objects. So while the object is fully occluded, this frisbee, the arm is not, and deep sort does its best to predict where the hand is and draw the bound around the person accordingly. The frisbee is in the hand, and therefore we now have an estimate of where the frisbee is when it disappears from view. This is exactly the idea that we work to implement as we retrofit the deep sort pipeline to a modified version of our original Kalman pipeline. With some additional tweaking and tuning, we find ourselves at a simple and elegant solution representation of where the object is behind the chair when occluded from the camera view, and our Kalman filter never deactivates. So we need to be clear that this solution is application specific and would most certainly require multiple color recognition and upgraded object recognition logic to work in a general scenario where you don't have straight lines like this.
Another one of our proposed approaches for handling occlusion is using shadow tracking to enhance the Kalman filter. This works with the understanding that as long as we have sufficient information about our light source, then the movement of an occluded object can be reliably tracked by using shadow, making the Kalman tracking much more robust. In pretty much every practical computer vision case, the light source tends to be fixed, for example, like sunlight or overhead lighting. As such, when an object has only horizontal movement, so will the shadow, right? Their center of masses will have the same quote unquote velocity. In addition, vertical object movement prediction can also be addressed by looking at the size and opacity of the shadow that the object casts as it moves closer or further from the light source. This object prediction, as it currently stands, still uses the original Kalman filter method of using the HSV to detect a shadow. However, we can make the shadow detection much more robust by moving away from HSV and using methods such as thresholding, background removal, or even deep learning. In any case, the shadow detection script is run in a loop by our main script, which is the flow that you see here, which predicts the movement of our object when it's no longer visible. Next slide. Um, So to conclude, the Kalman filter is fairly capable at tracking object movement, but has definite room for further enhancement and optimization. As we saw, deep sort performs object tracking very well, but can be further improved by leveraging our shadow tracking method, looking at what's actually causing the movement, and handling changes in resolution. The solution we've devised is very application specific, but a big part of solving computer vision problems is getting a full understanding of the data that you're working with and building an appropriate solution for that data. When fully realized, deep sort can have robust applications in real-time robotics and visual data collection. Thank you.
Oh yeah.